Buonasera a tutti. Ho il piacere di ringraziare, seduto qua accanto a me, Marco Wischmeier, group leader del plasma del Sol Modeling del plasma exhaust all'UPT, Max Planck, e anche project leader del Work Package Tokamak Exploitation. Noi sono 4 anni che Marco tiene queste lezioni, quest'anno abbiamo anche il nostro ospite per 3 giorni. Credo che sia una fortuna per noi, per i nostri ragazzi che potranno, diciamo, aver avuto questo piacere di aver avuto Marco qui ospite. Marco ci farà una carrellata di tutta la parte della Power Exhaust, sia modeling che poi anche i problemi in più demo. Alcune parti ricalcherà ciò che ha fatto già Sebastian Predischi, però ci serve anche un po' per rivedere tutto. Marco, lascia a te. Chiederei come vogliamo fare, facciamo 50 minuti pausa, 50 minuti, domande ti possono interrompere? Facciamo...
Soltanto per le domande, visto che io poi non
Sì, devi qui alzare la mano. Sì, Marco poi si interrompe. Marco farà la lezione in inglese, naturalmente, perché, come diciamo spesso non riusciamo a parlare di fusione se non in inglese, neanche io. Va bene, vai Marco. Tutto pronto.
Okay, 1 second, please. So I will sit here. Let me just organize myself. Okay, so there are a few people here. Hello. La maschera.
Sì, la vedo.
Okay, so now that I can breathe a little bit more, welcome to the lecture. My name is Marco Wischmeier, as Giuseppe already told you. So the title of the lecture, or the title of the series of lecture, is The Physics Basis for the Power and Particle Exhaust Problem of a Next Step Device. So this will be, let's say, a march through everything that is related to exhaust physics. So it's something related to how to protect these plasma-facing components that you see here. And I know that you have followed the lecture by Sebastian Brzezinski sometime this year, who talked to you about plasma materials interaction. So things like erosion, selection of materials for fusion devices, and material migration. And he also, in his lecture, touched a bit on exhaust physics, the concept of a limiter and the concept of a diverter. So I will see how you react when I reintroduce these concepts, so maybe it saves me some time. And I will start maybe just with a brief conceptual overview, because I do not know at which stage you are in your understanding, because sometimes you may have heard something in the lecture, but maybe you haven't had the time to revise it, or haven't memorized so far. So I think sometimes it's good to repeat. I hope I will not bore you, so I will look at your eyes and check if you are falling asleep or looking at the ceiling or watching your mobile phones. Those that are remote, of course, I cannot check what they are doing or if they have any interest. So, and please interrupt me if you have any questions. So as Giuseppe said, I'm in Garching. I did my PhD now I started my PhD more than 20 years ago in this area of research. And what you see here is the jet tokamak on the left side with its plasma-facing components. And on the right side, the plasma interacting with these plasma-facing components. And you see these illuminated areas. These areas is what this lecture is about. And that's why I've chosen this figure. So let me check. So I'll first start with a short motivation, and then I'll introduce you to the fundamentals or the fundamental physics relations that are important to understand and to grasp a little bit the Skripal layer physics. I will then introduce the numerical tools. That part will be a bit dry. I think we'll be there tomorrow. And I'll talk to you what we do with these numerical tools. So how valid is it to use them? And what is our understanding by using these numerical tools for interpreting this? And especially, why do we need a numerical tool in the first place if I have introduced to you today the fundamental physics relations? And I'll talk to you also a little bit what it takes to take the big leap and what it means, the big leap for the next step device. So you all know, of course, by now what is nuclear fusion. We have the one on the sun, and we deal here with the one on Earth in a magnetic fusion device. And I hope you all remember, but nevertheless, I repeat that you have, for the fusion on Earth, you have the fusion of deuterium and tritium, and they produce the helium and the neutron. Why am I showing this triviality to you? Because part of it is the fuel cycle that's relevant, and that's something that Sebastian talked about last time. So the neutron, you use it for the lithium to fission the lithium and to produce the tritium that then is reintroduced into your cycle. So what does this figure actually mean? This means that in order to go on with the fusion device or the fusion process, you need tritium. And for tritium, you need a gas injection system at the end of the day that extracts, so some system that extracts from the lithium the tritium, and then you need to inject this. And because you're continuously injecting deuterium and tritium, you also need to remove the gas out of the system. So it's a question of how well do you pump the system so that your fuel cycle, as it's called, is maintained and is in its optimum level. And then, of course, you also, well, you have helium being produced out of the lithium. Let's not worry about this, but you have the helium entering the system, and I'll talk to you a little bit about the helium in a minute. So, how is the energy produced? I hope you all remember that the electrical energy, or the concept of a fusion reactor, the electrical energy will be produced out of the, let's say, the moderation heat of these neutrons that will be absorbed by these breeding blankets. And then there's a water cooling system, so a heat exchange system that then runs a turbine, and this generates electricity. So this is, of course, a lot of energy, but we deal in this lecture not with the energy of the neutrons because they escape the system, they go into the breeding blanket. So that's, let's say, all part of engineering. I'm not an engineer. You are engineers, so maybe someday you'll work on breeding blankets. So this is an important aspect of a fusion reactor and by far trivial to solve. Yeah? Also because it's essentially nearly impossible in an experiment to test this because the fluence of neutrons that you have even in a future device like Eta, which I'll come to in a second, is not as high as what we will expect in a demo reactor. So a lot of this is based on principal concepts, numerical simulations, and the physics basis that needs to be validated to do this. So this is part of engineering. But here we deal with this part of the exhaust. So we produce helium, and of course, part of the kinetic energy, 1/5 of it, because the mass ratio is 1 to 5 for the overall mass. So you have 3.5 mega electron volts in the helium. This energy is kinetic energy that is in the alpha particle, and this alpha particle, through collisions, will slow down. I think I need to switch off my microphone, my speaker. And this energy, therefore, there's okay. So, and this energy is transferred to the plasma, heats up the plasma, and ultimately needs to get out, yeah, because the energy must stay somewhere. And this is what we call power exhaust. So, if we think of power exhaust and where we are, so what type of devices are we actually talking about? So our current experiments or the majority of the experiments is done in a small device that we call a medium-sized device, like R6 upgrade. So R6 upgrade is a device of about 1 meter 60 major radius. When we talk about major radius, this is the distance of the magnetic axis from the center of the torus. Then we have a machine like JET that's about 2.65 meter major radius, and then we have Eta with more than 6 meters major radius. So our experiments are done on devices that are a factor 3 to 4 smaller in major radius compared to a device like Eta that's supposed to demonstrate the physics principle of obtaining, let's say, in a longer pulse, more heat than what you put in to get it going, and a demo device that's even 1 scale larger. So if we look at Eta and demo, these machines will be of a similar size. Demo will be roughly at least a meter or so larger in major radius. Eta will have pulses of about 400 seconds, so that's why it's written 7 minutes. And the tritium that Eta uses will come by truck, essentially, or some means of transport from some fission reactor, probably somewhere in Canada that produces tritium. While demo and Eta only, well, let's say, only does physics experiments to understand or to validate the physics principles and define new operational regimes. But demo is supposed to produce electricity, and supposed to have a closed fuel cycle of the from the lithium to the tritium. So this may sound like a small step, but for power exhaust, and I'll come to this in a minute, from here, from our experiments to Eta is a huge step. And from Eta to demo is again another story. So this doesn't mean that the physics has nothing to do with it. So the physics or the dominant physics processes that we will deal in Eta and demo, at least from an exhaust perspective, are similar, just the magnitude changes. While the dominant physics processes from current devices to Eta, we are not sure how similar they will be in terms of which processes are the dominant one. Just keep this in mind. So a sketch of Eta, this is, I think Sebastian showed the same figure, so I'll jump over it. So as I said, Eta as this next step device is this international joint program between China, the European Union, Japan, Korea, the Russian Federation, the United States, and India. And it's this device of about 6 meters radius and this plasma current of 15 megampere and around 5 Tesla field. What you need to remember is that the fusion power is about 100 megawatt. So 100 megawatt of fusion power means how much power is ending up in the alpha particles and how much power is ending up in the neutrons, roughly. Any idea? Come on.
150 megawatt on the alpha power.
Probably a bit less, so 1 to 5. So yeah, but of the order, if you say it's around 100 megawatt, that's fine with me. Just that you have an order of magnitude. And then, of course, you see here there's external heating. So the external heating here says 73. So this is why if you now add 80, which it would be the power in the alpha particles plus this 70, you end up in 150 megawatt of power being delivered to the plasma. Maybe out of a curiosity. So I told you that in a properly working fusion reactor, it's a question, it's a bit diverging from what this lecture is. But just for you to also maybe understand why these numbers are like this. So why has Eta been designed to produce 400 megawatt of fusion power? Why not 200 or 100? or 1 gigawatt. Yeah, so the reason is you just estimated the alpha particles is about 80, 80 megawatt of power, and the external heating here is roughly 70, 50 to 70, let's say. So what does this mean? This means that Eta is the first device with dominant alpha particle heating. Yeah, there has been no device before. So even when JET will do, let's say, 10 megawatt of fusion power, you still have the dominant. So, and this is not even the alpha particle now, it's just the fusion power. The alpha particle is 1/5 of it. So you don't have dominant alpha particle heating of the plasma. Because the question that the physicists and engineers have is, how does the physics of the slowing down of this fast alpha particles influence things like stability of the plasma, the confinement of the plasma, and of course the power exhaust as well. This maybe just that you understand why 400 megawatts. And why not more? Well, because doing more is more difficult. And with 400, you are just, let's say, where alpha particle and additional and external heating are similar. Okay, this was just a small excursion. Now, if we ask a person like Gianfranco Federici, who is the head of the fusion technology department in Eurofusion. Eurofusion is this European consortium of the European labs, and ask, well, what are the outstanding technical challenges beyond Eta to go to demo? You see here there are the high heat flux materials, so this is what Sebastian talked about. Remote maintenance, which I do not know, you may or may not have a lecture. I think you had a lecture, or had a lecture, I think, on this. And the treatment reading blanket, as I mentioned earlier. But the diverter, and with diverter is meant the particle and power exhaust, is one of the crucial, let's say, problems to solve. Without solving this, we can't build a reactor like demo.
Yes, we had an expert from the mayor.
For treatment and maintenance, no? Yeah, because these are very engineering topics, these two, yeah. So this is why I'm talking to you about heat exhaust systems. So magnetic confinement, maybe just as a revision, this is the identical picture you saw from Sebastian's talk. I checked. So I will mostly talk about the tokamak principle, yeah. But there's of course also the stellarator. So as you will know, I hope, the stellarator is intrinsically steady state as a device, but has the complexity of a three-dimensional structure, and therefore also three-dimensional plasma-facing components, or at least having to think in 3 dimensions where to put the plasma-facing components that deal with the heat that comes out. And the tokamak is intrinsically a pulse device, maybe, depending on the physics properties, one could also do it a nearly steady state device. This depends a lot on the physics that is related to what we call current drive. But this is to be seen. Yeah? There is no proof. There are ideas, concepts, many smart people working on this. And these are the two, the physics that I will be talking about is in principle the same in the two devices. What I'm explaining to you can be transferred also to stellarator physics. There's no difference in the physics itself. There's mostly difference in the complexity and in what you need to remember and understand in order to see which are the relevant processes. The relevant processes in a tokamak may be different than in a stellarator. We are not sure. This depends a lot on the operational regimes, but could be. So I will focus on the tokamak because that's what I'm most familiar, even though, of course, the stellarator is also a device that's in the Max Planck Institute, and it's the Max Planck Institute in Greifswald, which is our sister institute in the north of Germany. So I talked to you about, oh, well, in this ideal world, plasma is confined on magnetic field lines. Yeah? So the charged particle gyrates around the field line and follows it, and then you see here the field line, these black lines here, they are ergodically covering a surface. Yeah? So this is then a magnetic flux surface. And in theory, they will be on this flux surface forever. Yeah? if there was not what we call perpendicular transport. And perpendicular transport can be a random motion due to collisions. Yeah? So this would be something like a bone diffusion, or also depending on your gyration radius, so that you collide with the particles on the next flux surface. Or, which is what we have nowadays, it's so this doesn't seem to work right. Let's see. Yeah. Or turbulent. So this is a very old simulation of a D3D discharge. The D3D is a machine similar to a 6 upgrade in size. And what you can see here are these filamentary turbulent structures, these fingers that go outward, and they cause a transport that's at least in orders of magnitude larger than the classical collisional transport that one would expect if you start writing down on a drawing board how transport works, which I will not do because that's, let's say, basic plasma physics course, which I don't know if you had or didn't have, but doesn't change life here at the moment. So for you to remember is that in tokamak, the main transport, let's say, to move particles and power radially outward is by turbulent transport, and turbulent simply exists. There are different ways how you can try to reduce the turbulent transport by some magnetic configurations or heating schemes. You can optimize things, but overall you should remember that this power that the alpha particles deposit into the plasma, so transferred to the deuterium and the tritium, will be transported outwards by means of turbulent transport. Okay. So, and then another small excursion, of course. So I mainly talked about power being transported outward without being very detailed at the moment, just conceptual. So this part of the lecture is more conceptual, so to set the frame. But of course, there's something else that needs to be transported outward. So this figure is maybe a little bit cryptic at the beginning, but in the core of the plasma, you have deuterium and tritium, and they do what? They produce neutrons and helium. The neutrons leave, they're not bound by any magnetic field, but the helium is trapped, and by the magnetic field, same as the deuterium and the tritium. So if I accumulate more and more helium, what does this mean for the fusion reaction? It stops. Well, maybe not stops suddenly, but it decreases. Yes. And what are the two reasons why it could decrease? So why does having more and more helium in the core decrease the fusion reaction? You know, our sun has a similar problem. Yeah, but you could argue that as long as you have reactions going on, you heat up the plasma. So you just need to have enough reactions, and then you would solve that problem. But you wouldn't solve other problems. Sorry? No, let's imagine an ideal world, only deuterium, tritium, and now more and more helium. So imagine you want to collide with a friend of yours, and another friend of yours always crosses your path. The probability to collide with your friend becomes less and less. Yeah? It's like at a party, you want to reach somebody else, and there are lots of people in between. It takes a lot more time to reach him. But if you need to reach him 10 times in 1 hour, you will not have a good conversation if the room is full of people, because you hardly make it 2 times over. Yeah? So this is similar for the deuterium-tritium reaction. Yeah? So the probability for them to collide decreases because they collide more and more often with helium. We call this fuel dilution. Yeah? It dilutes the fuel. The other reason is that helium has 2 positive charges, and so when you have 2 charged particles flying by each other, where they change the direction of their motion due to the Coulomb forces. What type? Do you expect any energy loss by this flyby of the two charged particles? In fundamental physics, you will have heard it. If you know German, it's obvious what it is. But so there's radiation losses called Bremsstrahlung. Brems means nothing else than braking. So it's like braking radiation. Yeah, means when you slow down. Yeah? So in this sense, when you change the direction of the path of a charged particle, it emits electromagnetic radiation. And if you do this, and if the charge of the particles is higher, then the directional change is larger because the force is bigger. And so you increase the Bremsstrahlung. And so you have this, if there's too much helium, far too much helium, then you suffer of too much Bremsstrahlung. And that's an energy loss because it's radiation, and this cools down the plasma. And so in the reaction rate coefficient, so there's an optimum for the fusion reactions at about 10 kilo electron volts, so a bit more. So if you cool down the plasma and you end up at 8 or so, then your DT reaction rate goes down by an order of magnitude. And then essentially at the end, your thing stops. Okay. So these, let's say the result of this is the radiation limit here. The result of this is that you have these, you will all have had the Lawson criterion, I think, at some point, as a fusion burn criterion that combines the density of the plasma, the temperature that is fixed, and the time you need to confine the plasma, which means it's the time that the charged particles need to stay in proximity so that enough reaction processes can take place. This is NT tau criterion, which is called the Lawson criterion. And you see this here on the y-axis, electron density, energy confinement time, time temperature, in units of 10 to the 20 kilo electron volts per second in cubic meter. So if there is no alpha particles, you get this fusion burn curve, and it shows you there's a minimum at around 11 kilo electron volt temperature of the plasma. And here you have these NE tau. Yeah? But as you increase the fraction of alpha particles, you see your burn curve moves up. And in this area here to the left, when you're left of these horizontal straight lines, then you're cooling too much. It doesn't work. So you are left with this small area of operation, which makes operating much more. And this is without any other impurities that may come in, yeah? Which Sebastian will talk to you about. Yeah? So you need to remove the helium, and the helium must be exhausted of the plasma, and you need to keep a fraction of below 10% of helium in the core. This is roughly the estimate that one has. You can also estimate how much helium you need to exhaust per second. If you know how much fusion power you need, you can calculate how many alpha particles this means you're producing, because each alpha particle has these 3.5 megaelectron volts. And then you can estimate, in order to stay below this 10%, how much helium you need to remove out of the system. And the helium that is produced in the core by turbulent transport, or also classical transport, will move radially outwards to the wall. And once it reaches the wall, you need to extract it from the system. And this means you need to pump it away somehow. So you need to have very efficient pumping. And this is not trivial because helium is not really a species that's easily to be pumped. So fusion exhaust must therefore maximize the pumping of helium ash. That's one of its primary tasks. It needs to provide sufficient pumping of hydrogen. Sufficient is always a very vague word in this context. But sufficient means to keep up with this fuel cycle that I told you at the beginning. Yeah? The deuterium tritium that you inject, you also need to remove the particles so that the throughput is constant. And of course, you need to minimize the damages to the wall. So Bastian Berenczek talked about erosion and melt processes, and these need to be minimized. So somehow you can imagine that part of this power, part of these 150 megawatt of power that's in the plasma, need to be removed before they hit the wall somehow. Yeah? So this is what we will be talking about, and you have already seen exactly this slide where the limiter concept is introduced. So in order to keep, so the yellow part is the hot plasma, where all the fusion in this idealistic way takes place. And this, what's this color, violet area is called the scrape-off layer. So why is it called the scrape-off layer in this context? Well, because somebody inserted a piece here that's the limiter, and the limiter does justice to its name. It limits the extension of the plasma up to the limiter and a little bit beyond in order to protect the vacuum vessel. So you can imagine this vacuum vessel here could be made of stainless steel, and the limiter of some material that you can sacrifice, and where the contact of the plasma with the material does not do too much harm to the center of the plasma. So usually we would use a low Z material, for example, so like carbon, because carbon may not produce too much Brennstrahlung in the core of the plasma once it's released. So why is it called this here scrape-off layer? Well, because the plasma is essentially scraped off there. Yeah? It's like a scraper being held in. And then this violet area has a certain width. Yeah? I can tell you it's very narrow, but I won't tell you at this stage how narrow it is. This is what such a limiter looks like. So you can see here, there is up here a limiter. We call this a colloidal limiter because it's in the colloidal direction. So turning around like this, we are looking at the colloidal plane of a cross section of a tokamak with a limiter. And this one here is the toroidal limiter because it goes toroidally. That's where the names come from. And then you can see here that the plasma actually interacts at the colloidal and the toroidal limiter. The interaction is visible where light is bright. So the problem with the limiter here is that this material here, once the plasma hits this area, gets eroded, and impurities leave this limiter and are immediately in the center of the plasma. So the probability of contaminating your plasma even more, we discussed the helium problem, but now you add up carbon, which can dilute and cause for radiative collapse. So you would need to limit this erosion, and Sebastian talked a lot about erosion processes as such. Yeah? So somehow the idea is, well, why not put the place where the plasma and the material interact far away from where the important part of the plasma is, which is the core, where all the fusion takes place. So the principal idea is, let's put the plasma wall interaction as far away as possible from the core of the plasma. And this is what the diverter does. So this is a discharge of a jet pulse. It starts in a limiter configuration. You can see the limiters lining up, but then it goes into what we call a diverter configuration. And now you have here the center of the plasma, that is the transparent area in the core. And down here, this very bright area is where the plasma interacts with the diverter. Yeah? So this is the diverter, and then at the end, it cools down. You can see now the diverter very clearly. These bright flashes that you saw during the discharge, these are called ELMs, edge localized modes. They're periodic ejections of material and power from the core. We will not really deal with them in this lecture here. So looking back now at jet plasma. So this is the figure from the title slide. So in the core, in the ideal world, we would have something like 10 kilo electron volts because we want to have fusion. Yeah? So we need this temperature. It's God-given. You can't have 8. You could have 14 or more, but that's more expensive to produce. So let's say 10 kilo electron volts. Then we have, you can see here, this illuminated line is very, very thin. Yeah? Imagine this thing here has a major radius of 2.65 meters. So this is the distance from roughly here, the middle, to roughly here where the K is. Yeah? So if this is 2.5 meters or a bit more, you can imagine that this is at most a few centimeters, not more. So this is an area that's illuminated. It's very thin. And then down here in the diverter, I'm telling you now, the plasma needs to have a temperature of 1 to 5 electron volts. For now, you need to take this as God-given. Later during the lecture, I'll explain to you why we come up with this number of 1 to 5 electron volts. Okay? So, how do we get there? First of all, we have this diverter. So, diverter means, you know that in the tokamak you have a toroidal current from the main plasma, that's part of the tokamak principle. But then one needs to create an area where, so in this yellow area, all the magnetic field lines, they eventually close on themselves. So you have closed magnetic field lines, and essentially a particle that travels on these can travel for infinite times along this. In this area here, because we need now to define an area where there's plasma-world interaction, we have what we call open field lines. Open field lines means the field line has a start and an end point. And the start and an end point is inside the wall. So for the plasma particle, of course, all magnetic field lines are closed. But when we talk about open ones, we refer to open from the perspective of an electron or an ion. Means that once the ion gets into this field line, it will hit a wall somewhere. Yeah? And where this takes place is down here in what we call the diverter. And this already, the name of this thing already has its function in it. Diverter means we divert something. Yeah? So we divert the plasma, the particles from, let's say, reaching here, this outer wall. We divert the plasma flow that goes into this violet area into this region here and hit down here and interact with the diverter targets, as we call them. And in order to do this, one needs to bend the magnetic field line. One needs to modify the magnetic field. And one does this by having, in this idealized case, it's just one coil, but in reality, there are many coils that go toroidally around. We call them the colloidal field coils. And a current is injected in here so that you create here magnetic null point. Yeah? And you break up the field lines essentially from this closure in themselves so that they are diverted into the walls. And so magnetic field line will start here. And then you remember that this is like a helix, the field line. So when I show you this colloidal cross section, you must imagine as if the field line starts out here, let's say in the wall, yeah? And then as a helix goes around your colloidal plane and hits the wall at the other side. So what is shown here is something like a flux surface, but the field line starts here, winds around and around and around, and ends up here. Okay? So for R6 upgrade, you see that the interaction is here. So this is, we call this green line here the last closed flux surface because it's the last flux surface that is closed in itself. Yeah, all the others outside are open. We call this line often also separatrix because it separates the core from the scraper layer. And we kept the name of this from the limiter times, which was scraper layer. So when the people introduced the limiter, they called it scraper layer. The name remained the same, even though it may be less of a scrape-off layer. It's maybe now more a diverted layer. Okay, so here you see R6 upgrade. This is still old times with other world material. You see here many little white dots in the picture. And yeah, this is again a sort of an excursion. Have you any idea what these white dots are? This is a camera image. Neutrons. Okay, so neutrons that disturb the CCD. Okay, talking about diverter, now let's look at what does this mean for Eta, just that you have an idea of what we're talking about. So this is the mock-up of an Eta diverter in its full size. Unfortunately, I don't have a human being here. The human being is about maybe like this piece here, just So this thing is taller than me as a diverter. So I'll give you some numbers in a minute. So this is again the concept of the diverter. I'm now introducing you with some nomenclature that we use when we talk about diverter physics, and later when I explain to you diverter physics as such. There's one area that we call upstream. Upstream is something, imagine like in a river, somewhere upstream. Yeah? And upstream is a location above this X-point area. Can be here, can be here. Often upstream is defined as the outer midplane. But for the concept, for what I'm going to explain to you later, it's any place above the X-point. Yeah? It doesn't matter where, it doesn't make much difference in the simple analytic approaches where this is. So this is one. And then if we look at the upstream location and we look at the plasma profiles, so we can, a plasma has a density and it has a temperature. Yeah? And so if it has a density and a temperature, it has a pressure. It has a plasma pressure. And what is plotted here is the plasma pressure as a function of what often the physicists love to use, normalized radius. So one is the position of the separatrix, and this is just 10% less referred to the major radius of the plasma. So you see here that when, just look at the red line, forget about the black one, not so relevant. So the H mode is what we call a high confinement mode, is where the plasma is well confined. It's well kept in its magnetic bottle. And if we look at the plasma pressure profile, it goes like this, and then there's a steep area here. And here we enter this dashed line as the separatrix, and then we enter this pivot layer. And this whole area where the whole pressure drops to low values is a few centimeters wide. So in eta, it's about 6, 7 centimeters. You must imagine this gradient here, 6, 7 centimeters of the 6.2 meters. Yeah? So that's the length or the size of where this gradient goes up. Yeah? Just to give you a perspective when we are talking about gradients. Now, the other area that I will talk to you about a lot is the diverter targets. So the diverter is down here, and the targets is where the plasma hits the wall. Okay, now I haven't looked at the time, but I guess Giuseppe will leave me here. So when did I start? 10:02. So let's say another 10 minutes, I guess. And then we'll have a break. So now let's put in some numbers and think of, okay, how big is this problem for Eta? These are slides from a good colleague of mine, Alberto Loate. So I'm trying to get my. So you have here, let's say, a schematic engineering plot from Eta. You see here in yellow the diverter. Yeah. You see here these green things, these are the ports where all sorts of diagnostics will be sitting. But our whole story happens in this area here. So here all the fusion burn process take place, and down here is our diverter. So in the conceptual graphics, you can see here, you have these about 120 megawatt of power. So that's, what power is this? This is the, what is labeled here P out is the power that crosses more or less this red line. Yeah. So this is the power that we put in from external heating. So these 50 to 70 megawatt of heating power. PA is the alpha particle power, so these 80 megawatts, so we get to about 150. And PRAD is the intrinsic radiation that you can't avoid, because even deuterium, helium, and tritium, they will produce Bremsstrahlung. Yeah. And you may have some intrinsic impurities because of the plasma-wall interaction. And so you estimate about 30 megawatt of radiation. So this leaves you 120 megawatt of power that will cross across this red line, so across the separatrix or the last closed flux surface, and will move towards the targets. Now, what does it mean it moves towards the targets? Well, moving towards the targets it means that the plasma is directed into an area that roughly covers only 10% of the total wall surface. So if we look at this in a bit more, I told you the scribble layer is very thin. Yeah? So these 120 megawatt, they enter the very thin scribble layer, which is plotted here in a schematic way. Now you have the human being. Yeah? So, and then it travels to the inner target and the outer target. Yeah? It can travel here in both directions, upway or downway. Plasma always travels towards the wall. Yeah? Ideally, always towards the nearest wall, but with some forces, it can also be going maybe to the wall further away. But as soon as plasma sees the wall, it will always travel to the wall. That's in the nature of plasma itself. So it will travel to, let's say, here the outer wall. You can see here this magenta arrow, maybe. That's the direction in which the plasma takes. And down here, this is now blown up. Is this thing here? This is the diverter. And you see here this color scheme without labels, which doesn't matter really. But this color scheme here only show you what is the surface area that's actually used of this diverter with which the plasma interacts. So, and this is about 1 to 2 square meters of the entire surface of the machine is used for the interaction. So this means if we split the power evenly, let's say between the inner and the outer diverter, then we can say, okay, the power into one diverter is about 50 megawatt per square meter then. Yeah, because if we say it's 1 to 2 meters and we have 120 square meters, then we end up with it roughly. Yeah? It's just to give you an order of magnitude. So, so what can we do about this? Actually, I think this statement down here is not fully correct. The surface of the sun is not 60, it's 80 gigawatt per square meter. And this, this comparison with the surface of the sun is often used for the heat flux actually up here at the outer midplane, where the scraper layer is only a few millimeters width. And then you have a power flux of this order of magnitude. Anyways, not so relevant. So how can we imagine this now? Now I come down to a schematic approach. Yeah? So what I'm doing now is I'm simplifying the problem so that we can deal with it and understand what the basic issues are. So I told you we have this upstream location and a downstream location. Yeah? So we have the inner target, upstream and outer target. So you can just take a feed line or what we call then a flux tube and stretch it out and make a slab geometry out of it. And as you can imagine, plasma loves to travel parallel to the magnetic field line because it's not, nothing stops it from doing so. Perpendicular to the magnetic field line, it gyrates around the field line, so it's bound to the magnetic field line. Doesn't like to move so much perpendicular to the field line. So the motion perpendicular to the field line is slower than parallel to the field line. But I showed you previously there's turbulent, so there is some motion perpendicular to the field line, but not as much as parallel. Yeah? So this is why we call it a competition between the fast parallel transport and the slower perpendicular transport. And this essentially makes your field line. So we have here now this idealized world. I split this up now. I only look at upstream to target. I don't care inner or outer target, just upstream to target. And this is what is shown here. So upstream, all the power comes in, and then it's transported to the target. The question is, how is it transported there? How does the heat from upstream reach the target? Yeah? And this is done by essentially conduction. So conduction means you don't need a particle to convect the power, yeah? But you just, one particle needs to hit the neighboring particle and transfers the heat through collisions. So it's a transport through collisional processes, and so it's a conductive transport. Yeah? So conductive heat transport, and in plasma physics, the heat conduction in the parallel direction is following this relationship from the Spitzer-Herrmann elaborated. So there's a heat conduction coefficient times the temperature, either ions or electrons, to the pi half, times the gradient of the temperature. So the steeper the gradient, the more heat is conducted, and the higher the temperature of the plasma, the more heat is conducted. The reason for this is because in plasma physics, the probability to, let's say, to have a collision decreases as the temperature of the plasma increases. This is a bit counterintuitive, but in plasma physics you can derive this. And this is the reason why with increasing heat, with increasing temperature, the heat flux or the capability to conduct heat goes up. Okay, and then we introduce something called L parallel. This is the connection length. It's the length of the connection between the upstream location and the target. Easy to remember. So now we distinguish ions and electrons. The heat conduction coefficient, kappa I, is smaller than kappa E, about factor 2000. Yeah? So this means in order to transfer, let's assume the 120 megawatt enter your strip over there. Half of it is in the ion heat channel and half of it was in the electron heat channel, just for simplicity. Then you would say, okay, then this means in the parallel direction, because it will not dissipate it instantaneously. In the parallel direction, once it got out, it goes parallel. I need to conduct the same amount of electron heat as ion heat. Yeah. So this is what is written here. QI parallel is similar to QE parallel. But because the heat conduction coefficient of ions is smaller than electrons, the logical consequence is that the upstream ion temperature is usually a factor 2 higher than the upstream electron temperature. Yeah, this is just essentially here to compensate for this number that's a factor 2000 smaller than the electron one. Right? And usually in experiments, we do measure ion temperatures in the scrape-off layer upstream that are about a factor 1.5 to 2, the very most higher than the electron temperature. Why am I telling you this? Because you shall not forget that this is the case. Yeah? Because now, from now on, for I think the rest of the lecture, I'll never mention this again. Yeah? Because for simplicity, to make everything simple, and it's just the question of the concept and not of the detailed quantification, we assume that ion and electron temperature are the same. Okay, just for simplicity. So this is the temperature, and then we look at pressure. P stands here for pressure, so the total plasma pressure. So the total plasma pressure is what we call the static pressure, so it's the product of density times temperature of electrons plus the static pressure of ions, so Ni times Ti, plus the dynamic pressure, which is if any plasma was moving, it would have a convective component, which I didn't mention yet, but you can imagine the plasma may even flow. And so it gets a convective component, a dynamic pressure, so this is the total pressure. We here don't care if it's static, dynamic, or whatever, just the total pressure. So I label with the lower T target and with the lower U upstream. Yeah? Now plasmas have a property. They conserve pressure along a field line. It's a fundamental property of a plasma along a magnetic field line. So if you forget what it's in brackets for now, this essentially reads the total plasma pressure at the target is equal to the plasma pressure upstream. Okay? Then we know that I told you that plasma always, when it sees a wall, it always moves to a wall. And the smart plasma physicists have found out at what speed it moves when it's very close to the wall. And the speed is the isothermal ion sound speed, which is roughly, I mean, it's not fully correct. It's actually, it's an adiabatic value, but for simplicity, we use this isothermal description here. So this contains the electron temperature, the ion temperature, the square root of it, and the mass of the ion. This is the sound speed of an ion that goes to the wall. So the plasma has the velocity. So if you have a plasma that's static upstream, once it reaches the target, it has sound speed. So the plasma accelerates between upstream and target towards the target. Yeah? And the ions get the kinetic energy. And this is, by the way, this kinetic energy is the reason why in Sebastian Besenschit's talk, he talked to you about erosion. And you need ions to erode, and they need kinetic energy to erode. And the kinetic energy they get from this acceleration process. Yeah? It's the same sound speed. We're talking about the same thing. So if we have a velocity of a flow velocity, this means we also have a flux of particles. And the flux is always something density times velocity. So the velocity is a square root of this temperature expression. And it can be formulated without me deriving here, is the particle flux to the target is proportional to the plasma pressure at the target divided by the square root of the temperature. This is what comes out when one reformulates it. So if I have a given upstream pressure from the plasma, then my particle flux at the target is defined. Because according to this equation here, it's the upstream pressure times the inverse of the square root of the temperature. Yeah? Because I told you to forget about the brackets of 1 minus F momentum for that. And then this means that the heat flux to the target, so the parallel heat flux to the target, is the total plasma pressure at the target times now the square root of the temperature. So the main difference is this is divided by the square root of the temperature, the other one is multiplied by the square root of the temperature. So now, question to you is, I don't want my target to melt. And you know, melting may occur if too much heat comes on. Yeah? You can melt anything if there's too much heat. So the basic question is, and this is where the equations are here, how do I stop the target from melting? Which knobs do I have? And this equation gives you the knobs. So there are two options. Either you reduce the temperature, because then the Q parallel goes down because the T goes down, or you reduce the plasma pressure. If you manage to reduce the plasma pressure between the upstream location and the target, then you reduce the power flux to the target. Okay, so two elements are there. Temperature, reduce the temperature, or reduce the pressure. And in order to reduce the pressure, there are many processes that can do it, but the loss or let's say the percentage how much pressure we lose on the way between upstream and target, we use here a terminology called momentum loss factor. So if F momentum is 1, then this means we're losing all of the pressure. Yeah? If F momentum is 0, no pressure is lost. And F momentum in reality will be something between 0 and 1. Yeah? But the more we manage to increase F momentum towards 1, you can imagine 1 never exists, but towards 1, the more we will reduce power to the target. Yeah? Or by reducing target temperature. Okay. I think I should have a break now, no?
Yeah.
So let's say we break until how long is the break? 10 minutes? Or?
5.
5? Then let's say we meet again at 10 to 4. Yeah. Okay. If you have any questions, feel free. Non ho fatto caso, ma non vedo domande.
Ok. Come dipende in continuazione del coordinate uguali. Benissimo.
È l'età diversa. Non soltanto barba bianca, ma anche chiari.
2.
No, 1.
Scusate, mi sentite? Sì, vorrei fare una domanda,
certo,
se è possibile, se potete rispondermi voi prima che
certo.
torni il relatore. FMOM che cosa indica?
Adesso ci arriviamo. Diciamo, il fattore di perdita di pressione.
Ah, ok.
È un
Quindi,
valore tra 0 e 1. Cioè 0, nessuna pressione persa, 1, tutta la pressione persa.
ok, grazie.
Poi per
Ah,
adesso è soltanto un numero.
ne deve ancora parlare, ovviamente.
Esatto. Ok?
Ok, grazie.
Okay, so if there are no other questions at this time, we'll continue. So we were just talking about this pressure balance and that you need to lose pressure because you want to reduce the pressure at the target, because the pressure at the target will reduce the particle flux to the target, and it will reduce most of all the heat flux to the target. So, but before we come to the story of pressure loss, you just, for now, you need to remember that the holy grail is how to lose pressure. So let's come back to what is the width of this scrape-off layer? Yeah? What do we know about it? So good colleague of mine, Thomas Eich and colleagues, already now 10 years ago, they did several measurements in plasma conditions where they assumed there is no pressure loss along the feed line, so pressure is conserved. So usually these are diverter plasmas that are relatively hot. And they took measurements of the footprint of the heat flux onto the targets using infrared cameras. They did very precise measurements. And they came up with a scaling law using various plasmas in various devices. So this is just jet and A6 upgrade, but for different isotopes, for deuterium, so helium and hydrogen, and A6 upgrade deuterium. And then tried to fit a curve through this cloud of beta, which is this black line. And they came up with a scaling law that says that the width of the plasma, so the distance over which it decays to 1 over A, so from the exponential, assuming an exponential decay, scales as proportional to the power entering the scrape-off layer. Forget about this minus 0.02 because this is essentially 0. So this means the width of the scrape-off layer is essentially independent of the power entering the scrape-off layer, yeah? Because something to the 0 is 1, not dependent. R to the 0 is also 1, so it's essentially not dependent on major radius. But it's dependent approximately inversely proportional to the colloidal magnetic field. So that's the colloidal magnetic field, yeah? Not the toroidal magnetic field, but the colloidal magnetic field. And what produces the colloidal magnetic field in a plasma mainly? The toroidal current. Yeah. So the higher the plasma current, the higher the colloidal field. So a machine with more and more toroidal current has more and more colloidal field, means the lambda Q is getting smaller and smaller and smaller. What does this mean when I showed you initially the picture of A6 upgrade, jet, and Eta? A6 upgrade has a toroidal current of roughly 1 megampere. Yeah? Jet operates at 2 to 3 megampere, but can go up to 4 megampere. Yeah? Eta will operate at 15 megampere. So you can expect that the lambda Q in Eta will be a lot smaller, according to the scaling law, than what we have now on jet or A6 upgrade, roughly speaking. And then times more or less the square root of the elongation. Epsilon is an elongation, tells us how far the plasma is from being round. So a circular plasma would have no elongation, and the more it becomes, let's say, stretched, the more it becomes elongated. Yeah. And Eta is on top of it also, compared to current devices, a strongly elongated plasma, which adds to reducing the lambda Q. Okay, so this is a scaling law that we came up. And now we can think of what is the parallel heat flux. Yeah. Now that we know how wide the flux tube is, in which the power is, we can estimate what the heat flux density is. So how much power per square meter do you get? So in order to know this, you need to take the power that you have divided by the surface area of the cross section of this flux tube in which all the power flows. And how do you know what the cross section is? Well, this, I won't go into the details because this is more or less geometric magnetic field line relations. But it's essentially this, the A parallel is 2PR colloidal field times lambda Q, the width, divided by the total field. Yeah, that's the cross-section surface of such a flux tube. And so, the Q parallel is essentially this. And so this you can now eliminate a few terms, and you get to that this is proportional to the power entering the scraper layer times the toroidal field divided by major radius. Yeah? So at the end of the day, your parallel heat flux density goes up with toroidal field, goes up, of course, with the heating power that you have, and goes down with increasing radius. So, but going to larger radii seems sort of obvious, because you, yeah. So, if we look at this now, so the Q parallel upstream is the power. Just to go back, yeah, this is the power. The heat flux that is upstream at this location where this lambda Q is defined, because that's the definition upstream. So it tells you what the power flux is here. And now this power flux travels to the target. The question is, how can we reduce the power flux to the target? And for this, we look first here to the right side. This is a cross-section of MAST. So this is a smaller compact device in England, spherical tokamak. So it has a very small minor radius. That's why it's such a compact device. And you can see here in blue the last closed flux surface, and in red is just one feed line that winds around the machine. And at some point it hits the target. Yeah? You can see that it doesn't hit the target perpendicular. It hits the target apparently on some angle. Yeah? And this is why people incline the target, because what we're talking about here is the parallel heat flux. But what the material scientist or engineer at the end of the day is interested in is how much is the power flux perpendicular to the target. So how much really hits the target per square meter. Yeah? Because otherwise you have the projection onto the perpendicular. So this is why we need to know what the incidence angle is. This theta target is the incident angle between the magnetic field line and the target component. And so the perpendicular heat flux is, of course, the parallel heat flux projected onto the target. Yeah? So projections are always done by the sinus. And the angle of incidence is, it is set at best about 2 to 3 degrees. So it's a very shallow angle, usually not much more shallow. Yeah? Eta has an impact angle of about 4 degrees. So this means, if you make the sinus of these 2 to 3 degrees times the parallel heat flux, this means you have reduced the perpendicular heat flux compared to the parallel one, just by inclining the target by about 80 to 100 as a factor. So this is why one tries to incline the targets and have as shallow as possible field lines. I'll come back to the problem of shallow angles later in the lecture, not today, maybe tomorrow or the day after. I'll discuss why there is a limit on these 2 to 3 degrees. So now that we know what the perpendicular heat flux is, we can ask the engineer that builds the component onto which I put my heat flux and ask him, listen, how much is the heat flux that's allowed to get onto this target before this melts away or gets destroyed or vaporizes? And he will say, okay, the maximum heat flux you're allowed to put on here is Q perp max. So, yeah. So if I know what the parallel heat flux is, and I know what the projected perpendicular heat flux is, I know how much power I need to dissipate at least to reach this maximum allowed perpendicular heat flux. Okay, so this F min dis is a dissipation factor. It's something between 0 and 1. Again, like the F momentum, it's a value between 0 and 1. So it can be 0 if I don't need to dissipate any heat. Yeah, and it will be 1 if I need to dissipate all of it. Okay, so this is the, you need to get used now for the next slides, but to this terminology, the minimum dissipative power fraction. And the derivation is, it's what would you have if you didn't do anything as perpendicular power flux onto the target compared to what you're allowed to. Yeah? And the quotient or the ratio of the two gives you the dissipation factor, the minimum dissipation factor. So where does this heat flux or this Q perp max, where does this come from? So let's look at diverter components as such. Some of it was done in the lecture by Sebastian, but we'll get back to it. So let's look at what does this mean for a machine like Eta or Demo. What value are we talking about when we talk about Q perp max? So this is again the nice cut design of Eta, and now we come to the Eta diverter. Eta diverter will be, so this is the diverter structure. So you have here the inner diverter, then here you have the outer diverter, and this thing here in the middle, they call it a dome. Yeah? There's a debate if you need or don't need a dome. Some people think for diagnostic purposes, others for plasma physics reason. But for you, important is this inner diverter here and outer diverter. This whole thing that you see here is called a diverter cassette, because the idea is that here on the right, you would have several cassettes, so components of already, you mount the diverter outside of the machine, you put everything together in a cassette, and then like in a cassette, you just move it in, and then on rails, you move it into toroidal direction, and you put it into position. So if one diverter breaks, or part of it breaks, idealized, is that you take out the cassette, yeah, and you replace it by a new one. So, of course, there's nothing that you do in 24 hours, yeah. So don't break the diverter cassette, even though they're made of cassettes. Eta will have 54 cassettes. So 54 of these elements. Each element weighs roughly 9 tons. Yeah? Now, you can see here, maybe a little bit vague, but down here there are little tubes here going in. And then you see here, it's not one piece, it's made of little blocks. Yeah, I'll show you in a minute how these look like. But these are single monoblocks, they are all water cooled. And we have about 4,300 of these small water cooled blocks overall. And this system altogether is called a plasma facing component because it's composed of several items. So it's composed of the monoblock, it's composed of the water cooled pipe, it's composed of the technology to drive the water through these things. And the Eta diverter has been qualified for accepting heat fluxes of 10 to 20 megawatt per square meter. Okay, this means our Q perp max in Eta is 10 to 20 megawatt, more on the 15 side. Okay, this means that for a machine like Eta, your Q parallel that comes in at the top needs to be reduced to a value of Q-perf of about 15 megawatt per square meter. And you remember I gave you before a number that was roughly 50 to 60 megawatt per square meter, because the wetted area was 1 to 2 square meters. P sol was 120 megawatt. So we have 60 megawatt per square meter, and this needs to be reduced to 50. Okay? So this is in Eta. I'll not talk about the tolerance of the monoblocks here. Let's compare a few numbers. I know you saw exactly the same slide from Sebastian. So you get about half a kilowatt per square meter when you lie in the sun in summer. If you are a shuttle tile, so now the shuttle doesn't really exist anymore, but historically, so the heat protection tiles that you would have here in front would do about 500 kilowatt per square meter heat load. Yeah. The Eta main chamber, so this is all the other components, they do about 5 megawatt per square meter, 3 to 5 megawatt per square meter. And the Eta Diverter would do roughly 20 megawatt per square meter, just to give you a bit of a relation what we're talking about. Yeah? So the heat flux of these diverter components in Eta need to deal with a lot more heat than the shuttle engine. Yeah, and you all know this dramatic picture of everything blowing. Plus, the heat shield of a shuttle is usually a one-way ticket, let's say. Afterwards, it's dismantled. Only needs to last one entry. So, if we now think not just about Eta, but beyond Eta for the materials, a further complication comes in, because in demo we have a real fusion reactor that produces electricity. So it will have many more nuclear fusion processes, which means it will have lots more neutrons than Eta. Yeah? The thermal heat of a fusion power plant like demo will be of the order of 2 gigawatt, while that of Eta is about 400 megawatt. Yeah? So it's factor 5. And this means it's a lot more neutrons. And the neutrons, when they enter the material, they can cause damages from interstitials or replacements of the grid structure. So, but I think Sebastian talked about this quite a bit. And this causes a further restriction on the engineering and the choices of these components. And so what is shown here is a demo type water-cooled component. So what the concept is of such a demo, you see again these monoblocks now. And you see here the water pipe. And then because these are made of tungsten and the pipe is made of copper, there's some alloy in between, which is copper chrome zirconium, because otherwise tungsten and copper wouldn't bind. And this type of a monoblock for demo will do with 10 to 15 megawatt per square meter. So in current experiments, it tested up to 15 megawatt per square meter, but it's expected that with the neutron damage, it's roughly more around 10 megawatt per square meter. Now, this means that the plasma flux in demo, not only do we have a bigger machine, but the restriction is even bigger on the thermal flux. So instead of 15 megawatt per square meter, we can only deal with 10 megawatt per square meter. And now we make a rough estimate. Something you don't know yet, but will know as the lecture goes on. The plasma radiates, it radiates electromagnetic energy. And the electromagnetic energy will hit also the plasma facing components and deposit energy on there. Yeah? It's like, yeah. So part of the energy that will reach these components will be electromagnetic radiation, light, X-rays, and stuff like this. And this contributes already in Eta, 2 to 3 megawatt of the power reaching the components of the diverter are radiation. Yeah, not neutral, just normal radiation. So if we have a component that's only made for 10 megawatt per square meter, and we need to reserve some for the light that reaches it, so 2 to 3, and then maybe there are also some neutrals, because not all the plasma will carry the heat, but the neutrals may also carries some heat, let's say 1 to 2 megawatt. Then what you're left with what the plasma can actually deposit, so our Q perp from the equation, because that was just plasma, ends up to be about 5 megawatt per square meter, because the rest is taken up by the radiation that takes place, the neutrals that are there. And so you have more power that you need to dissipate, and you need to dissipate it to much lower levels than Eta. This is where what I mentioned at the beginning, while the physics between Eta and demo may be similar, the magnitude of the problem is a totally different one. Yeah? So this makes demo even worse in a certain sense. So here you see Astex, Eta, and the fusion power plant. So we call this EU demo 1, about 9 meter radius, and the perpendicular target geometry with 2 targets and not doing anything about dissipation. Just what you have as heating power, let it be and let it reach the target. Would mean that for Astex upgrade, when we have the maximum heating power, so there's no heating from fusion, that's just the heating we have from beams and electromagnetic heating like ECRF and ICRF, amounts, so the total heating of Astex upgrade is about 25 megawatt, and due to the small wetted areas where in the diverter, this translates to about 40 megawatt per square meter, if we assume that the power is equally shared between the 2 targets. For Eta, this means about 100 megawatt per square meter, and for demo, this would mean 350 megawatt per square meter. You remember that I just told you that the demo target will only be able or allowed to take on about 5 megawatt per square meter. So you need to reduce this 350 to 5. That's our task in this lecture. Okay, easy task. And this is why this is still considered a showstopper, because we do not know if we are able to do this on a demo scale. And that's why it's an area of active research. Yeah? We don't have a clear answer yet. So what does this mean in terms of minimum dissipation? You remember this is this F min dis, the ratio of the Q perp max that you're allowed to, divided by your projected heat flux. So for Astex upgrade, this means we need to dissipate about 50% of the power. Yeah? For Eta, this means we dissipate about 80% of the power. And for demo, this means we dissipate about 90 to 97% of the power. Yeah? Now imagine you have 2 gigawatt of fusion energy, 500 megawatt of, so this means of this 500 megawatt, you need to dissipate in the volume something like 450 megawatt. Yeah? Then you're at 90%. So that's the power story of the whole thing. Yeah? But there's also another story that's related to the particle flux to the target. So I showed you earlier that there's this, just back for a second. Oops. So here you have the heat flux. Yeah? So we know that the perpendicular component of this should be 5 to 10 megawatt per square meter. We also have a particle flux. Why is the particle flux important? Because the particle flux tells us how many ions reach my target per second per square meter. And you learned that each ion, if it has enough kinetic energy, can erode material. So if you don't limit the particle flux, the lifetime of your diverter is very low because you erode it very fast. So if you want to prolong the lifetime of your component, you need to reduce the erosion. Why do you need to reduce the erosion? Because if you have, let's say you look at this component here, this here is maybe a centimeter and a half or 2. Yeah? So as you start eroding this material, this distance becomes smaller. As the distance becomes smaller, the temperature gradient between the top and the water cooling pipe changes because the heat is conducted in this component. As it's changing, the amount of heat that it can handle will change. Yeah? And so your erosion will have an effect on how much power this component can handle in time. Yeah, when you put it in, it will handle a certain amount of power, and after several years, it may handle 30% less, yeah, because you've eroded part of it, and the conduction is changed, and so on. Okay, so we talk about erosion here. So that's why material erosion as a limiting factor. So just a recall, yeah. So what is erosion? So you have plasma impacting the material, it interacts, and then the plasma can be reflected, yeah, or it can bury itself into the material itself, so it diffuses into the material, or because it thermalizes, after a while, it will resurface again. And once it's at the surface, if it overcomes the adhesion forces on the surface, the gas will just leave the surface. Yeah? So if the component is hot enough, then the gas can more easily leave the surface because the kinetic energy of the gas is higher than the binding energy of the adhesion forces. Yeah? So this causes recycling. But for our components, the problem are erosion here. So because it just kicks out particles from the component. And then you have impurities that can go into the plasma, which is bad for the plasma. You lose part of the material in one location and you will deposit it somewhere else. Okay? And then you have another effect here that's not so relevant for the component lifetime as such, but this is the tritium co-deposition. Because when you bombard a material with deuterium and tritium, and part of the fuel diffuses into the material, also part of the tritium will diffuse into the material and will be stuck there and will be extracted from the fuel cycle. So you've produced tritium with lithium fission in the breeding blanket, and then you lose it in the material. So this is why when Sebastian explained to you the material properties, one of the criteria was to select a material that minimizes the tritium co-deposition. Otherwise, you pile up a lot of tritium that you don't really use, which is bad for machine safety, and it's also bad for the overall fuel cycle. Okay, plasma wall interaction can take place all over the place where the plasma interacts with the wall, but in our case, we now limit ourselves to the diverter. And then you can, furthermore, when you have high energy particles, they can produce these vacancies, yeah, and interstitials. And this changes the thermal properties of the material. Yeah? And furthermore, when you have neutron bombardment, because you also have the neutrons that reach the material, then neutrons, which is not in this picture but written here, the neutron that hits a tungsten atom, yeah, at some point can also trigger a fission of the tungsten. And this produces rhodium and chromium and so on. And so over time, from pure tungsten, yeah, there's a nice simulation that I didn't bring, but you can see how over time, from pure tungsten, you end up with 2 to 3% of the tungsten after 2 years not being tungsten anymore, but fission derivatives of tungsten due to the neutron bombardment. And this, of course, also changes the thermal properties. We all know that even for iron, yeah, small quantities of an additional metal, like chromium or so, or vanadium, will change the properties of iron drastically. Yeah, this is the principle of steel, yeah, to have a certain amount or fraction of other spurious elements in there. So you can imagine the spurious elements in tungsten will change the properties of tungsten. And this changes the thermal properties. So I'll skip this because you already did this in a different lecture. So looking again at erosion. So here is the yield per hydrogen. So this means what is the probability, let's say, to release a tungsten atom from the material surface if a hydrogen atom hits it. Yeah? As a function of the temperature of the plasma just in front of the target. So you can see from this that the higher the temperature, the higher your erosion yield. Yeah? All the curves go up. But you can also see that if you say, okay, if the yield is below 10 to the minus 5, I consider no erosion taking place because there's such a small number that it doesn't really matter. Yeah. So you can see that for the pure deuterium, you can allow yourself 50 or more electron volts before you sputter tungsten. However, the problem is we want to cool the diverter. I told you earlier that we need to reduce the target temperature. And I told you there's radiation, and I told you we need to dissipate 90% of the total loss power of the demo device. So how do we cool this? And we'll come to this in a minute, but we inject impurities. We inject argon, nitrogen, or krypton into the plasma because they're very efficient coolants. But the problem is they are very efficient specimen to erode tungsten. Why? Because argon, nitrogen, and krypton, they're much, much heavier than deuterium. So if they have the same temperature, they have a lot more kinetic energy to transfer to the tungsten at the same temperature. And this is why, while deuterium is here, yeah, for krypton, you need temperatures below 10 eV are sufficient to start eroding. But what you can also see from this figure, that if you are in a low temperature region here, let's say around 5 eV or less, then also even with impurities, the erosion becomes minimal. So essentially you can say you're not really eroding much, or the likelihood is very low. And so this gives a motivation to have target temperatures below 5 electron volts to minimize erosion, and looking at this, even maybe below 2 to 3 electron volts. So you have now two boundaries. One is stay below 5 megawatt per square meter in demo, and below 15 megawatt per square meter in Eta. And then in demo, furthermore, minimize the erosion and stay below 2 to 3 or 5 electron volts. Yeah? This is the boundary condition. So the reason for the temperature here is not only because of this equation, Q parallel equal to P target, so target pressure times square root of temperature, but also because of the erosion. Okay? So, because of the low erosion yield of tungsten in the recent decade, let's say, several devices have changed to high Z components as a material. So, Alcator CMOD, which isn't operating anymore, was a machine that was covered with molybdenum, which is a high Z material, not compatible with neutron irradiation, but for the machine itself, it was fine because they just needed a high Z material. JET has moved to what they call the Eta-like wall, so tungsten in the diverter, beryllium in the main chamber, which is a low Z material. And ASIC's upgrade is a machine that's completely made of tungsten, target and main chamber, and so is more similar to demo in terms of its, at least of the material that the plasma sees, yeah? Not the components, because there are no, the components are not really water. Okay, so now we come to the actual physics of how do we reach this dissipation of power and momentum. So I told you that we introduce impurities. Why do we introduce impurities? Well, what is plotted here is what we call a cooling factor. So the total radiation of an impurity is the electron density times the concentration or the density of the impurities, Nz. So when you see a Z, it's usually some impurity of charge Z. Lz, which is this cooling curve I'll describe in a minute, which you see on the left, that is something of a function of electron density, electron temperature, and the time that the impurity spends inside. Yeah. Times a length if it's along a line of sight. So, the cooling factor now. So, forget about the units, yeah, the small unit doesn't matter in this context. Because NE will be 10 to the 20, NZ will be 10 to the 17 or something like this, so you get enough power from this. But you can see that for hydrogen, the cooling curve is very low. It's the red low curve compared to all the others. So the cooling efficiency of radiation from hydrogen is not very much. You can imagine this because it only has one shell. Yeah? For radiating, what is very efficient is if you have an atom where you can excite and spontaneously decay electrons often. Yeah? The more line radiation you can produce, the better. The more you can use it for cooling. This is why you see these high Z materials like tungsten, xenon, krypton up here, because they still, even at high temperatures, they still have bound electrons. While here, the other curves, you can see here, this does a continuous line. Yeah, so this there's no shells anymore to populate or depopulate when you're above a certain temperature. Okay, this means this thing here starts to be fully ionized to a large fraction. So you have for the different species, you have different cooling curves. You see here, nitrogen is very efficient at low temperatures. Also, argon is very efficient at low temperature, even krypton. Some are less efficient at high temperature. Yeah? You see the curves follow a little bit different functionalities. And now you inject these impurities into the plasma. One of the questions that the physicist will ask himself at some point is how much of these impurities end up in the core and disturb my fusion process because they radiate in the core, and how much will these impurities remain in the scrape-off layer and in the target. Understanding this is part of current research. Yeah? We don't have, at the moment, simple scaling laws that tell us that if we put in nitrogen, then it gets compressed in the diverter by a certain factor. We don't have a proper scaling law for this at the moment. We are understanding how this works in a tokamak depending on various discharge conditions. After this little excursus, so you can pick, depending on what machine you have and at which temperature range you want to radiate your power, you can pick which species you use. And this will then enter here, your formula will give you impurity radiation. Then we define the fraction of impurity radiation as the ratio of how much power is radiated from impurities divided by how much power comes in at the top, yeah, the Q parallel upstream that we have. This value will always be smaller than the total dissipation of the plasma. Why? Because part of the dissipation is also transport. So perpendicular transport outside of the field line. Q parallel is all the heat parallel to the field line. But I told you there's turbulent transport perpendicular, and this will also remove power. Yeah? So, and this is part of dissipation because this power that gets transported by turbulent transport perpendicular to the field line doesn't reach the diverter, it reaches somewhere the main chamber. Okay? So, but what you need to remember here is you can inject some impurity, nitrogen, neon, argon, or krypton are the major candidates, and you radiate power. Okay? So, what else happens in this scrape-off layer? So we inject impurities, we start radiating power. If we radiate power, the scrape-off layer starts to cool down. It will have areas where the scrape-off layer becomes cooler and cooler and cooler the more impurities are able to radiate. So if we have the power entering the scrape-off layer, and this is just a pure schematic, we have an area where we inject these big green impurities, yeah? And they start to radiate. So this is H times nu. So we have a radiating region. In this radiating region, you produce a temperature gradient, the plasma cools down. And then at some point, the plasma is cold enough that you will have neutral particles. So imagine an ion, a deuterium ion hits the target. It gets recycled or reflected, so it comes back as a neutral particle into the plasma. Yeah? This neutral particle can be immediately reionized if the plasma is hot enough. So the ionization potential of deuterium or hydrogen is 13.6 electron volts. Yeah. So if the plasma is 20 electron volts hot, this neutral atom will be reionized nearly instantaneously. Yeah, the mean free path is very short. But if the plasma is very cold, let's say it's just a few electron volts, 1 or half an electron volt or 2, then because you need 10 electron volt to ionize it, a single collision with an electron will not instantaneously ionize it. Yeah, it will collide with one electron. This electron will excite the electron that is inside the neutral, because the hydrogen has one electron. Yeah. And then maybe if it doesn't hit an electron for a while, this excited electron de-excites and emits a photon and cools down the plasma by doing so. Or it hits another electron, which excites it again. And we call this step ladder-like ionization. So step by step, the electron is excited to higher levels if the electron density is high enough, until it eventually gets ionized. But this means you do many collisions, yeah, before you actually ionize. And so there will be regions where you have neutrals that are somewhere in the plasma and play a role. And then you can have a region where neutrals and ions collide. Okay, they do so-called charge exchange process. Charge exchange means a deuterium ion collides with a deuterium neutral and becomes a deuterium ion and a deuterium neutral. Yeah, they just swap. But what is the important part of this swapping? The ion that comes is following a field line. The neutral that comes is not following a field line. Yeah? The ion that comes from the plasma has a high temperature. So it has a lot of kinetic energy because it has a high temperature. It collides with a neutral, and because they have equal mass, it can transfer essentially all of its kinetic energy to the neutral particle. Now you have a neutral with a lot of kinetic energy. But this neutral is not bound by magnetic field lines anymore. The ion was, but the neutral is not. And so the neutral may be leaving the plasma, maybe not. Yeah? Maybe it's just flying in the wrong direction because it was kicked in some direction so that it meets immediately another ion, maybe one of the slow ones, yeah, that have been produced, and retransfers its energy back to the plasma. Then the plasma hasn't really lost any energy. It has just done a complicated way of transforming energy. But occasionally, these neutrals will leave the magnetic field lines and hit the wall, and they will deposit energy onto the wall by charge exchange. Not only this, we had this ion that was moving. It collides with the neutral, and the ion slows down by this collision. Slowing down means it has lost kinetic energy and momentum. Losing momentum means losing pressure. So charge exchange neutral collisions are one of the ways to remove momentum, not only power. Yeah? So here we are dissipating energy and momentum. So in this area here, with the radiation from impurities, we're dissipating energy. We're cooling down the temperature. We're reducing T, the temperature component of the pressure. But this may mean that we increase density. In this area here, we can start to remove pressure because we can transfer pressure, kinetic energy, from ions to neutrals. When the plasma is cold enough, and we're talking about temperatures of 1.5 electron volts, roughly, yeah, in this area, there's one more process that starts to play a role if the density of the plasma is high enough, and that's volumetric recombination. Because you can ionize neutrals, you can also recombine ions. And volumetric recombination is made of two processes. One is radiative recombination. So this means an electron falls, gets bound again, and you emit a photon. And the other one is three-body recombination. This means you have an electron, second electron, and an ion. One ion recombines with one electron recombines with the ion and forms a neutral. But due to momentum balance, the momentum is only conserved if you have a third particle, which is a free electron, and this gets some of the momentum transferred, and then you produce a neutral. This is a very efficient way of recombining ions when the temperature is below 1.5 eV, and when you are at densities above 10 to the 20 per cubic meter. At these densities and temperature, the recombination rate goes really up. It's higher than the ionization rate. And so you create a zone which we call the recombination region, where the plasma recombines in the volume. What does this mean now? The recombination, we already learned that charge exchange is a way to remove pressure and power. But recombination is even better. Why? Because you remove an electron and you remove an ion. You remove two particles at the same time. Yeah? And they're taken out of the system, essentially. Yeah? They fly along the same trajectory as the original ion, are recombined and then hit the target somewhere, but they hit it as a neutral. And there are no more charged particles. Yeah? So once the ion has recombined, it doesn't feel the acceleration field anymore at the target. So it's not accelerated to sound speed anymore. The flow velocity doesn't increase anymore, it decreases. Yeah? So you end up having energy in the neutrals. That's why I said when we talked about 10 megawatt per square meter of the demo component, don't forget there will be neutrals that will have energy, and these are the neutrals that will have energy. Yeah, the charge exchange neutrals and the recombination neutrals that reach the target, they carry still kinetic energy, but the probability for them to erode material is essentially zero, because these particles are not accelerated by the sheath, and so they can't gain enough kinetic energy to kick out a tungsten atom. Yeah. So recombination is the dominant momentum removal process once it's acting. It's only acting when the temperature is low enough and the density is high enough. The other one is charge exchange process. And the third one that I haven't mentioned yet is perpendicular transport. Because if plasma moves in the perpendicular direction, it moves particles. And which means if you first have a high pressure on a feed line at your strike line, where the plasma just gets out of the core and hits the target, if you have a process that moves plasma in the perpendicular direction, it spreads momentum. Yeah? It's not focused anymore on a small surface. You make it as wide as possible. And so you spread the pressure over more feed lines. Yeah? And the consequence is that the peak pressure cannot be the same anymore, because if you have the same total pressure, you are redistributing it. So the peak pressure will go down, which means you reduce the particle flux to the target. So this is just to show you the myriad of volumetric processes that can exist. Yeah, you don't need to look at all of them. It's just to show you what type of process we are taking into account when we do our work. So you have atomic ionization here. You have, this is here charge exchange. This is dissociation of molecules. Here, for example, you have dissociation of ionized molecules. And then you have also concatenated processes. So where you need first one process for another one to kick in. These are, for example, molecular assisted ionization. So you start with a molecule. It does a charge exchange process with an ion, which produces an ionized molecule and a neutral. And then this ionized molecule hits an electron or gets hit by an electron and dissociates by being ionized into a deuterium ion and another deuterium ion. Yeah, so from a molecule and one ion, you produce two ions. So it's an ionization process efficiently, which is why we call it molecular assisted ionization, because it starts from molecules. Okay. So what do we not know about all this? So if we want to know how much impurity radiation we can have, or we have, we need to know from the formula, we need to know what the temperature of the plasma is, what the electron density is, and how many impurities there are. If we have all these three informations, we know how much power the impurities will radiate. But this is not a trivial thing, because usually we look at impurity radiation by means of spectrometers. Spectrometers are things that look along one line of sight. So you have a lens and you have your spectrometer, and the lens collects all of the light in its path. But you can imagine that if I look across here, I capture light from here, from here, from here, from here, from here. Yeah? I do not know, I would need to know what the temperature is here, and here, and here, and here, and here, and here. Yeah? But I don't have all this information. Yeah? The lack of information is often our biggest problem. And so this is why this is called a spectroscopic challenge, because often we don't know what the concentration or the impurity density is. It's very hard to find methods to evaluate this. Then we can't inject infinitely impurities into the plasma, because due to core radiation being too high, it can become too high. There's a limit on how many impurities are allowed in the core. Yeah? So there's a limit on core impurity density because of fuel dilution and radiation. Similar to the discussion we had at the beginning for the helium. It exists also for any other impurity, just worse, because they are higher charge state. So actually there's a better publication than this. So this was an EPS project, but there's an actual real paper from 1 or 2 years ago, 2 years ago. So then, if you want to limit the impurities in the core, you can also maybe try doing this by compressing them as much as possible in the diverter. So to try to have a high fraction of impurities in the diverter and a low fraction of impurities somewhere upstream or in the core. Because the impurities, the density is not equal in the whole space. Yeah, there are forces like friction forces that can confine impurities into the diverter volume and keep them there. Yeah? So that the impurity recycles on the target, but hardly gets out of the diverter. Yeah, you can try to make the plasma conditions such that this happens. And there are some scaling laws. So some people have tried to come up with simple relations, and it seems like with higher magnetic field, you favor impurities to be compressed. Okay. So it's good to finish here at this stage. Yeah, so I'll stop here for today. Because then we put the pieces together. So you know now the principle of momentum removal for this F momentum. You know now the principle for dissipation for this minimum dissipated quantity. You know you need radiation for this. So now we have all the components in principle that we need for the next 2 lectures. The question is just, what are the processes? How do we identify them? How do we interpret experimental data? And what do we know? How important is actually volumetric recombination or impurity radiation in real plasmas? And what can we say from what we know today about how a machine will perform in the future? So what areas of research are there? So today we're setting the stage, and the next days we look at the real components. Okay, thank you very much. Are there any questions? I can't see. The outside world is quiet. Yeah, I destroyed all the listeners.
Question from outside?
Maybe tomorrow
Okay.
they get some courage.
Okay. See you tomorrow.
There's a question.
Okay, question.
I don't know who.
Dominic.
Yes, thank you. My question is the following. that is presently in the somewhat small machines we have, it is necessary to use impurities to radiate enough. But apparently already with a jet machine, there are regimes where a high radiation can be obtained in the diverter without having any impurity seeding. So when looking toward much larger machines like Eta or Demo, would it be possible to dream about a diverter which would radiate enough without impurity seeding?
So I need to correct you there a little bit. So at jet, it's not that the diverter radiates enough without impurities. I mean, either you have intrinsic impurities because the diverter is so hot from the plasma that you erode tungsten and then the tungsten radiates.
Yes.
Or what you can do is, in order to protect the diverter tiles, like in a machine like jet, what you can do is, in order to avoid that the heat load is all the time at the same place, you can move the strike line along the target, and we call this sweeping. And by sweeping over the target, you distribute the power over a wider area. It's like saying, okay, let's say I have 10 megawatt per square meter focused on 1 centimeter radial length, but if I distribute this over 1 second, over 10 centimeters, then I have, on average, over 10 seconds, reduced my average power by a factor 10.
Mm-hmm.
Yeah?
Okay. Okay.
But in order to really dissipate power, so in a machine like Demo or Eta, the strike line is fixed because it's essentially, or many people think, it's impossible to do continuous sweeping, and it wouldn't be sufficient to dissipate this amount of power, or to redistribute this amount of power.
Okay, but in the jet, you told me that there are always impurities which are radiating, but I was wondering whether it might be possible to operate the machine without having impurity seeding, without adding more impurities than those which exist naturally. What do you think about that?
No, because the erosion rate in a machine like Demo would have to be so large, and you are only allowed to have a concentration of tungsten of about 10 to the minus 5 in the core.
Mm-hmm.
So this would be impossible. You would destroy your target to radiate enough power, because I told you, you need to dissipate about 97% of the power. Mm-hmm. Dissipating 97% of the power means you need to radiate about 70%, because the rest is done by transport.
Okay.
And 70% of radiation you really need to go here for argon, krypton, and so on.
Okay.
Unless you go to alternative diverter configurations where maybe the radiation requirement is lower. But I'll come to this maybe next time. So,
okay. Okay. Thank you very much.
But from this curve alone, you can see that hydrogen is not sufficient as a radiator compared to the others.
Okay. Okay. Thank you.
Okay, is there any other? No? Then I'll see you next time.
Okay.
I pause or stop?
Stop.
Stop.